What's up, guys? Welcome back to the YouTube channel. Today we're going to be continuing the series on mathematical induction. As I said that I'm realizing I really sound like a YouTuber. Anyway, we're going to jump straight into the questions. They're different from last video's questions. So the first question: prove that 2 to the n is greater than n squared for each integer n such that n is greater than or equal to 4. So firstly, we always start with the basis step. Test whether it is true for the first element of this set here. That's it. So let's just say left hand side is equal to 2 to the 4 is equal to 16. Right hand side is equal to 4 to the 2, which is equal to 16 also. Therefore 2 to the 4 is greater than or equal to, I guess you could also say left hand side, but whatever, is greater than or equal to 4. I guess maybe your teachers might be pedantic, so you have to say 16 is greater than or equal to 16. 2 to the 4 is greater than or equal to 4 to the 2. Therefore 2 to the n greater than n squared holds true for n equal to 4. Okay, guys, so what I want you to see here, is that some people may be confused as to why you can say this, why you can say that it's greater than or equal to. I need you to understand when it says greater than or equal to, it means, yeah, the or, that the or equal to is important. Yeah, it's either greater than or equal to. It could be one of the two. Yeah. That's basically the inductive hypothesis. This is just where we basically just write this thing here in terms of case. So we want to say assume. It's important that you say assume or some synonym of assume. Assume that 2 to the k is greater than 2 to the kth, as some have said, is greater than k squared for some integer k greater than or equal to 4. And then onto the inductive step. This is where we test whether it's true for k plus 1. So let me just write out the heading and then we'll start with the full. Okay, here we go. Test whether that is true. So let's just underline it just so that the marker doesn't think that we, starting our proof of there. So we say left hand side is equal to 2 to the k plus first, as my one professor says we should say. Anyway, then what I want you to see here is that this is basic algebra, basic laws of exponents. To when you have some exponents, sorry, the basis should actually be the same. When you have two exponents of the same base multiplied by each other, it's just equal to the sum of the exponents, the base to the power of the sum of the exponents. So that's why you can do that. And then here, what I want you to see is also, for example, if I say 2a, that's just equal to a plus a. So 2 times 2 to the kth is equal to 2 to the k plus 2 to the k. And then what I want you to see first, you just try to, since this is unclear, it's unclear how we're going to get from here to there. So try to simplify that term, right? So let's just simplify that term. It's just so we can get like a general direction of where we're trying to go. So what we first notice is that there's nothing in common between these two. There's actually nothing in common here. So we need to look at what we've been given. So what we have, so firstly we look at the inductive hypothesis and we look at the restrictions placed on the set. So looking at the inductive hypothesis, we see a way that we can convert the 2 to the k into a k squared, right? So let's do that. So we say this is greater than, since it says greater than or equal to, we say greater than or equal to here as well. We say that's greater than or equal to k squared plus k squared by the, sorry, let me just remove this and put it up here, k squared plus 2k plus 1 by the inductive hypothesis. Okay, and then now we have a k squared and we have a k squared there, but we don't have this term. But so what I want you to also try to get in the habit of doing when doing these types of questions is looking at all the available information. So going back here, we see that n is greater than or equal to 4. The k is also therefore greater than or equal to 4. So what we can do is we can try to convert one of the k's into a 4. Convert, quote unquote, right? That's not very mathematical language, but yeah. So firstly, we're going to say that is equal to k times k, because k squared is equal to k times k. That's just the definition of a square. It's a number multiplied by itself. And then what I want you to remember is how k is greater than or equal to 4. So what you can say here is that that whole term is greater than or equal to k squared plus 4 times k. Now, for a lot of people who aren't familiar with this type of, this type of proof or this type of doing this type of thing, this seems very weird. For me, when I first saw this, I thought that this was what I called mathematical shenaniganery, right? Because how can you do such a thing? But what I want you to understand is that as long as this expression here is greater than that expression there, basically anything goes, right? So you can say since k is greater than or equal to 4, yeah, that's the reason. Yeah, so we have k squared plus 4k. Now to get the 2k, we just break the 4k into two 2k's, right? 2k plus 2k plus 1. That's just basic algebra. Sorry, I don't know where that 1 came from. I'm getting ahead of myself. And then, so for some more mathematical shenaniganery, we're going to remember that k is greater than or equal to 4. And then we're going to say that since k is greater than or equal to 4, we can say that 2k is greater than or equal to 4 as well, right? Because it's greater than, so it fulfills one of the requirements of being greater than or equal to. So therefore, 2k is greater than 1. We can say that k squared plus 2k plus 1. Now, I know that seems very counterintuitive, not even counterintuitive, it just seems outright ridiculous. You can say since, I'll continue my explanation just now. Since that handwriting is terrible. Since k is greater than or equal to 4, therefore 2k would be greater than 1. That seems weird, but like I said, as long as this here is greater than that, and that's why doing the inductive step of mathematical induction requires some out-of-the-box thinking oftentimes. So it requires a lot of practice, and also, if I'm being honest with you, I would have never thought of this myself. I saw it in a question paper memo one time, and I said, oh wow, that's cool. And yeah, that's where I learned the technique. Anyway, you want to simplify because you want to get this term here, and then that's equal to the right hand side. Therefore, we can say 2 to the k plus 1 is greater than or equal to k plus 1. And also a word on the signs here. We're proving that it's greater than or equal to. So that means that in here, we can have equals to signs, we can have greater than or equals to signs, and we can have just strictly greater than signs. The same goes for if we were like proving something is less than or equal to. However, if it just said greater than, then we would have to have at least one strictly greater than or equal to sign. Otherwise, we would not be 100% sure whether it's strictly greater than or equal to, or just strictly greater than or equal to. I recommend if you're having a tough time understanding that, maybe watch that part of the video again, or go write this out, try it yourself, convince yourself of it, and yeah, it can be very hard to understand, but yeah. Okay, on to the next question. Question 2: prove that n to the power of 3 is divisible by 3 for every non-negative integer n. So let's just write that in a different way. Let's first think about what does it mean to be divisible by 3. It means that n minus n can be written as 3 multiplied by t for some integer t. Right? For some integer t, that means there's some integer t that can be multiplied by 3 that will give us this. Or it also, right, just to maybe make that a bit more intuitive, n to the power of 3 minus n all divided by 3 is equals to an integer. Yeah, that's just the definition of being divisible by 3 or being divisible by a number. For every non-negative integer, let's just say for all n non-negative, just n greater than or equal to 0. Right, it's important that you include the equal to, because then if you don't, then your basis step will be incorrect. So we're going to start off with a basis step, and then let me just write the basis step, and then I'll be okay. So here is the basis step written out. Let me just move it a little bit down just so that it's a bit more legible. Test if n to the power of 3 is equal to 3t minus n is equal to 3t for some integer t for n equals to 0. In terms of the English there, I don't know, but I think it should make sense. But anyway, so we're gonna do our regular LHS. Left hand side is equal to n3. Actually, let's just substitute it straight away. Minus 0 is equal to 3t. It's equal to 3 times 0, and 0 is an integer. Oh, no, we don't even have to say what's it, that 0 is an integer, therefore, right, okay, actually, maybe for those of you, that's equal to 0, and then you can say 3, anything times 0 is equal to 0, so obviously you can say 3 times 0, therefore, in that, for some t element of z holds true for n equal to 0. Okay, now on to the inductive step. Sorry, not the inductive hypothesis, yes. Where we're going to assume that k to the power of 3 minus k is equal to 3. What should we call it? Should we call it 3t as well? I feel like calling it a different thing. Let's call it 3p for some p an element of z and k. Did I say some integer k? Some integer k greater than or equal to 0. Did I say greater? Yes, okay. For all, yes, I should just include that, and it's an integer there. Okay, so then we're going to do the inductive step, and with this inductive step, you can't do the usual thing where, like what we did here, where we simplified this one like on some rough work, which you can then erase after. There's only one side that you can actually work with, so this might be a bit more tough for some people, but yeah, I'll be back when I'm done writing the heading stuff and all. Okay, there we have the inductive step written out. Test if k plus 1 all to the power of 3 minus k plus 1. Important to note, you can't say that without the brackets. That's because of the distribution law. You can't do that. It's equal to 3p for some p in elements of integers and some integer k plus 1 equal to 0. Okay, so we're gonna start here. Let's just underline it so that any pedantic markers might not have a problem with us. Remember the brackets. Remember the brackets. Okay, so firstly, what looks good to me is to simplify first of all, so that we have something to work with. Okay. You could simplify this step by step, breaking it into k plus 1 and then k squared plus 2k plus 1 and all that. But if you know like Pascal's triangle and all that, then you can just, skip ahead. And what we want to do, right? We want to try to use, you're basically always going to use the inductive hypothesis. So we want to try to get this term somehow. Sorry. We want, this expression rather, those two terms. So we note that we have this and we have this. So we're going to bring them together. Plus, instead of simplifying fully, right, We're going to bring those together. The ones can cancel. We don't really care about them. And what we see here is that we're already starting to see multiples of 3, right? K squared is an integer. K is an integer. So this part of the expression is already a multiple of 3. It's already divisible by 3. So what we're going to say here is K to the power of 3 minus K is equal to 3P is equal to 3P. Ooh, maybe we shouldn't say P here. Maybe we should use a different letter. Let's just say Q. Some Q and elements of Z. Yeah, just so that we don't get, confused with using different variables with the same name. So we see that we have the 3's here, and that's just equal to 3. What you want to do is you want to factorize the 3 out to make it apparent to the marker that this is, you should say by the inductive hypothesis. I'm just going to abbreviate it, but you shouldn't do this. Yeah. So, and we can say, and P plus K squared plus K is an integer. Therefore, I don't know if you have to say this whole Q thing, but yeah, therefore, yeah, I think you could possibly even leave it out and just say divisible by 3. Therefore, K plus 1, 3 minus K plus 1 with the brackets is divisible by 3. And then you would need to write a conclusion. And also in the previous question, you should have written a conclusion as well. Conclusion, K, what was the original question? Oh yes, n to the power of 3 minus n is, rather maybe actually you should write the full thing and say, therefore, by the principle, actually let me write it out there now. Therefore, by the principle of mathematical induction, n to the power of 3 minus n is divisible by 3 for all non-negative integers n. This video is getting quite long, so I don't know if I want to have a third video. I think I'll have a third video in which I go over further examples, but that has been all. Thank you very much for watching, and please consider liking and subscribing. Share this with people whom you know need it. And that will be all for this video. See you in the next one.